Hello, my name is Theresa Trinh, and I'm a senior majoring in chemistry. And today I will be talking about the integrated lab research that me and my colleagues did on the electronic effects of p-Phenyl substituted substituents on the electrochemical oxidative 𝛼-Thiophene dimerization. As the concern for climate change has increased throughout the years, research involving renewable and non-carbon emitting energy like wind and solar have become more important. And so the focus of this research is to determine a way to store energy efficiently and for a long period of time. And so a promising system is using solar energy to drive a non-spontaneous 𝛼-Thiophene dimerization reaction, which has been previously researched by Heinz and his co-authors. And so non-spontaneous reactions are reactions that usually require more energy input or a catalyst to lower the activation energy in order for them to occur. So in this case, solar energy is the source of additional energy. And so Heinz researched this mechanism here, and so the solar energy would be driving this reaction and storing energy in this carbon-carbon bond. So using cyclic voltammetry data, Heinz hypothesized that the Thiophene dimerization reaction followed this three-step mechanism shown in this figure here. And so the authors proposed that the mechanism began with a one-electron oxidation of the Thiophene monomers, which is the loss of one electron. So as we can see here, it leaves one electron and then this positive charge here. And it would be followed by a dimerization reaction where two monomers react with each other to make a carbon-carbon bond. And then it would end with a rate-limiting deprotonation, which is the removal of these two protons here and leaving this product here. And we can see in this figure that there are many cationic intermediates, which are compounds with positive charges in this mechanism, as shown here and here. However, there is a lack of structural evidence that further supported this mechanistic hypothesis. So in our research, we aim to provide evidence that either supports or disproves the Heinz mechanism. Some Carroll College researchers synthesized the Thiophene monomer compounds that we use for this research, the methoxyphenyl-thiophene and the ethyl ester phenyl-thiophene. And so in this figure, this R prime here represents the different substituent groups. And so the one in red is the methoxy group, and the one in blue is the ethyl ester group. And so the ED stands for electron donating, and EWD stands for electron withdrawing. And so we made a 30 micromolar solution of each thiophene monomer in tetrabutyl ammonium hexafluorophosphate and acetonitrile, and we use cyclic voltammetry and UV vis spectrometry to monitor and measure the potential values of the compounds. So cyclic voltammetry, or CV, obtains data through an instrument called the potentiostat, which allows us to track the movement of electrons. So in an atom, electrons are negatively charged particles that can interact with other electrons to make bonds. The loss or gain of electrons in a reaction is known as an oxidation-reduction reaction. And so an example of cyclic voltammetry is shown here. UV vis spectrometry is used to measure the absorbance of a compound by shining UV light on it, which has more energy than visible light. And so every compound has a specific absorbance wavelength called lambda max. And so it will show up as a peak on the spectrum at that particular value. So for example, in a reaction, the reactant will have a different peak than the product. And so the UV vis can track the progression of the reaction. So in theory, the reactant peak should be decreasing and the product peak should be increasing because the reactant is turning into product. An example of a UV vis spectrum is shown down here. And so by using both cyclic voltammetry and UV-vis spectrometry at the same time, we can monitor the progression of the dimerization reaction as it occurs in real time. And we perform multiple CV runs with different potential ranges to monitor the changes in potential. And so we started off with a positive 0.5 to a negative 0.8 bandwidth, and then increased the positive voltage by 0.5 for every run until we saw a prominent oxidation and reduction peak. So in our CV graph, the positive potential values correspond to the oxidation over here, and then the negative potential values correspond to reduction over here. And so for the ethyl ester phenyl thiophene solution, we saw that there were prominent peaks at about 0.1 volt, shown in blue here, where we could see that there was a corresponding change in the absorbance of the UV-vis spectrum. There isn't a sure way to know if a peak on the CV represents the oxidation of our desired compound, so the UV-vis was a way to see when there was an oxidation occurring. And so looking at the UV-vis spectrum, we can see that oxidation is occurring at the peak around 270 nanometers here. And we can see that it increases over time. So this red line here represents the absorbance at 34 seconds, and this green is 171, and so on. And so we can see that this peak is increasing over time. However, this oxidation may not be the dimerization reaction of the ethyl ester thiophene, because the steady state, or the lambda max of the monomer, is at approximately 300 nanometers, which is right here. And so this dotted blue line represents the steady state, or the lambda max of the ethyl ester monomer. And so theoretically, we should be seeing a decreasing peak corresponding to the reduction of the monomer at around 300, but we don't see that here. And so this inconsistency may be due to the concentration of the ethyl ester thiophene solution being too low, and therefore the dimerization reaction is occurring at an undetectable amount. For the methoxyphenyl thiophene solution, we saw that there was a peak at about positive 0.8 volt, which is shown in red here, where we could see that there is a corresponding change in the absorbance with the UV-vis. And so looking at the UV-vis spectrum, we can see that there's a decreasing peak that occurs at the steady state of the methoxy monomer, which is shown by this dotted purple line here. And so we can see that this is decreasing as time increases, as time progresses. And then there's increasing peaks at around 332 nanometers right here and 650 nanometers right here, which may correspond to the oxidation of the monomer and therefore formation of the dimer. And so this red shift of the product is consistent with what we would expect based on the increased size of the pi conjugated network in the dimer. So looking at the overlaid CV and the UV-vis spectrum, we determined that the methoxyphenyl thiophene had a less positive potential than the ethyl ester phenyl thiophene. So looking at the CV, this red corresponds to methoxyphenyl thiophene, and the blue corresponds with the ethyl ester phenyl thiophene. And so we can see that the methoxy group has a more negative, a less positive voltage than the ethyl ester does. And so we hypothesize that this is occurring because the methoxy group on the thiophene is more electron-rich and is therefore more oxidizable than the ethyl ester group. And so this hypothesis is further supported with resonance because the methoxyphenyl thiophene can donate its lone pair of electrons to stabilize the cationic intermediates of Heinz's proposed mechanism. So this figure here, we can see that The oxygen on the methoxy group can readily donate its electrons and distribute it throughout the structure, and therefore stabilizing this positive charge. And so we can see that the oxygen can share the positive charge in the structure. And so therefore, the more electron donating the R group, the faster the reaction, and vice versa, the more electron withdrawing the R group, the slower the reaction. So in this case, the more electron donating is the methoxy group, and the more electron withdrawing is the ethyl ester group. And so looking ahead, we plan on determining the rate constants for these two compounds for the purpose of performing a Hammett analysis, which is a linear plot of reaction rates based on the electronic properties of the R group. Thank you for listening to my SURF presentation. Have a great day.